let's continue our conversation on operator overloading. But now we want to discuss when we should make these functions class member functions. So recall C++ permits us to define operators for our class. So we can specify how operators should behave on classes that we define, and we can write our own operators for binary operators such as plus, minus, multiplication, for comparison such as equals, not equals, less than, greater than, for assignment, and we're going to get to assignment next time because we need to talk about copy semantics before we do that, and also for the insertion and extraction operator. And those are usually used in order to determine how should your objects be printed or read from IO streams. Now, when we want to write an operator as a member function, once again, the name is the word operator followed by the symbol for the operator. So here we are going to look at our implementation of the operator class. And the big difference when we actually use a member function to implement an operator, to overload an operator, it's the implicit assumption that the left-hand side is the this object for which the function is being called. So recall that this is the self-referential pointer, which is this object is calling this member function. And let's see what we mean by this in main. So we have declared C1 and C2 as our complex numbers. And then we want to add C1 and C2 and save the result in a complex number C3. So what I meant by the left-hand side is the left-hand side of the plus sign you'll see is the object C1. So when the operator plus is called, it is going to be called on the C1 object. And the right-hand side, C2, is going to be passed in as the parameter. So that's it. So the left-hand side is the complex object for which this function is being called, C1 in this case, and the right-hand side is going to be the complex object that is being passed to the function, in this case, C2. So that's the right-hand side is the argument. And then you can see that it returns a complex object. So we add C1, which is this, and we add it to the right-hand side object, C2, and we store the result as a complex object in C3. Now, let's see what this implementation actually looks like now, is that now that it's a member function, and we can see the declaration of which we just discussed, now that it's a member function, it can access the real and imaginary private data. So now it just, once again, instantiates a local complex number object, and then it adds the real and the imaginary parts of the left-hand side and the right-hand side, and stores the result in the temporary objects, real and imaginary respectively, and then it just returns the temporary object. Another way to make this more clear is that when we are doing this statement here, another way we could have written this if we wanted to make it more clear is we could say, okay, temp real equals this real. So that's the left-hand side object. Plus the right-hand side object real. And you'll notice that in this example, we left that off, and it's entirely fine. But that's what is implied when we leave it off, is that the left-hand side is this object, the object for which this function is being called. And in particular, in the example in main, is, as we mentioned, this object would be the C1 object because it's the left-hand side of the plus operator, and C2 would be passed as an argument. Okay. So we just implemented when we want to add together two complex numbers. But now we want to think about how can we add a complex number and an integer. So here we have C1 and C2, and now rather than storing the sum of C1 and C2 into C3, we want to take C1 and add the integer 2 to it. And you'll notice that the compiler is going to be upset because it's going to be looking for a right-hand side, which is an integer. It'll notice, wait, that's not a complex number. That's an integer. So it's going to see the C1 object is the left-hand side. It's going to look for a member function, which has as the right-hand side argument an integer. It's not going to find it, so it's not going to compile. So it's actually looking for a function as a member of complex of the form, the name operator, plus, but you'll notice now the right-hand side should be an integer, which is the right-hand side. Okay. Another thing I wanted to mention that I wasn't so clear about just a moment ago is that you'll notice that the operators that we're implementing are const functions, and that is some of why we're returning a complex number, because we don't want to actually change the left-hand side or the right-hand side of the argument. We want to just make sure that the object on which this function is called and the object which is passed as the right-hand side parameter are not changed. That's why we're returning a complex object and saving it. Okay, so now we need to implement our function which has the right-hand side argument as an integer. Okay, and here's the signature that we were looking for. We have a complex number returned. The name of the function is operator plus. It takes as the right-hand side our integer, and once again, it's a const function. And all this means is that it is not going to change the complex number object on which it is called. So now to implement this, and this is our responsibility where it's not inherently clear to what part of the complex number should our integer be added. So we're making an assumption, well, if we're passing an integer, we want it added to the real part and not the imaginary part. So that's what we do. We create a temporary complex number. We add the right-hand side integer to the real part of this complex number. And I just want to make this clear again. So this could also be written as this real. And this can also be written as this imaginary. And so we take the real part of the object for which we're calling this function, and we add to it the right-hand side and save it as the real of the temporary object that we'll return. And then we just copy over this object's imaginary value to the temporary complex number's imaginary value, and then we just return the complex object that we had just created. Now, inside main, the compiler is looking to call C1 because C1 is the left-hand side object to the plus operator. So it's trying to call on the object C1 the function operator plus with an integer. It sees that that is defined in the class and implemented. So now it works completely fine. It will save the results of adding 2 to the real part of the complex number C1 into the complex number object C3. Now, with binary operator overloading, the one thing you may have noticed is that we were very, very careful to create an object, a temporary object inside the implementation and return that object. And the reason for that is that we want to make sure that we are not changing the left-hand side object or the right-hand side object. And another reason for this also is that's why we put const, and this is why we also made them const member functions. The const member functions is what made sure we could not change the left-hand side object. And then you may have also noticed that we were passing in the right-hand side complex object by reference also. And that was to make sure that we didn't change the right-hand side object. So I just want to go back slides and highlight that for you. right here, you'll notice that we protected the right-hand side when we passed it by const reference. So this is what we are referring to. We make it a const member function, so we can't change the left-hand side object. We pass in the input parameter, which is a complex object, by const reference, so we can't change the right-hand side. So that's why we had to create this temporary complex number that we returned. And you'll notice with ints, we didn't have to worry about const because we were just passing it as a value. Oh, moving ahead. So that's why we made the copies when we were actually implementing them, is we wanted to make sure that the left-hand side object and the right-hand side object of the operator were not changed. So that's why we had the copy. And we just want to highlight that when you implement operators for your own classes, they should obey the normal order of operations and associativity as they would for any other data type. So this is getting into the thinking that any classes that we write should behave as though they are native data type in C++. And it turns out that the operators can be overloaded with different right-hand side types, and they may actually be necessary, as we just saw. We saw an example where we overloaded the plus operator with the right-hand side being a complex object, and when the right-hand side had to be an integer. So let's just review what this looks like now. So inside of main, we have our three complex objects we declare. We have C1, C2, and C3. And you'll notice that we want to add them all together and store the result in C4. So what's nice about this is that the compiler will actually chain those calls from left to right. So the first thing the compiler will do is the compiler will add C1 plus C2, and then the return value, it will call the plus operator on the return value and add the complex number C3 to it. So that's what's happening here. So it's actually doing two calls to the operator with different objects. The first call is on the C1 object. The second call is on the object returned from adding C1 and C2. And then that object has its plus operator called with the object C3 passed to it. So that's what's actually happening. And you'll notice that the function being called for this, the signature being called, is the left-hand side is a complex object and the right-hand side is a complex object. So here that is being called twice, and you'll notice that this is what is also being called for C3. So when we add C1 and C2 and store the result in C3, we are calling the function which has as the left-hand side a complex object and the right-hand side a complex object. But on the next line, when we want to take C3 and add an integer to it, we are calling the next implementation where the left-hand side is a complex number and the right-hand side is an integer. And the compiler searches for those overloaded definitions of the operator in order to compile. It turns out that we can even define our own relational operators for our classes that we write. So we can overload relational operators such as equal, not equal, less than, greater than. And these operators should return Booleans. And in this specific example, we want to implement what equals. So inside main, you'll notice that we declare C1 and C2 complex numbers. And then inside the if statement, we want to check if those two complex numbers are equal. So what should that mean? That's what we have to assign. So usually we think two complex numbers are equal if their real parts are the same and their imaginary parts are the same. But I just want to mention that when the compiler sees the statement right here is C1 equal C2, it is going to be looking for an implementation of the operator equal, which we have right here. And it will want the left-hand side of the operator to be a complex object and the right-hand side to be a complex object, and it has to return a Boolean. So because the left-hand side is a complex object, it's perfectly fine to make that a member function. And then when we implement this member function, we just code exactly what we had said. We just compare the real part of the complex number, this complex number, to the right-hand side, and the imaginary of the complex number to the imaginary of the right-hand side. And just again, just remember that we could have done this comparison by going this real. And recall that this real is the left-hand side, and this imaginary is the right-hand side. So recall that the left-hand side, so excuse me, is the left-hand side. That the left-hand side is of a member function of the implementation of an operator is always the left-hand side. So whenever you have a member function, an operator that's implemented as a member function, the left-hand side is always the object of that class. And you can pass whatever you need for the right-hand side. But when it is a member function, the left-hand side always has to be type of object for which it is a member function. So that's why we just showed that that's what we mean by the this is implicitly there with the left-hand side object.